Hello, and thank you for attending this METTLER TOLEDO safety webinar. My name is Stephen Rowe, and I'm the Managing Director for DEKRA Organisational and Process Safety in the UK. Over the next half an hour, I'm going to show you a case study that we worked with one of our clients on, where we retrospectively proved the process safety of a very hazardous epoxidation reaction, and we learned a lot, some really good lessons to share. Before I delve into the detail of the case study, I'll just briefly introduce DEKRA Organisational and Process Safety for those of you that may not know us. In our business, we deal with technical process safety, that's the prevention and control of fires, explosions and accidental chemical releases. And in the organisational side of our business, we also deal with behavioural change consultancy aimed targeted specifically at high hazard industries. In our work, we do a lot of process safety and regulatory safety testing, process safety consulting across a whole range of topics that make up process safety. We offer competence development training schemes for our clients to help educate and upskill in all the areas of process safety. And we do organisational leadership and workforce diagnostic assessments to look at the culture of organisations, their leaderships and their engagement of their workforce to help them plan a strategy to improve reliability in the human domain. Finally, we do psychological and cognitive consultancy, drawing on insights from neuroscience. We use a brain-centric tool to help us reduce risk. Before we start, it's really important to acknowledge the operating company who have very kindly granted permission for this paper to be published, and we really thank them for enabling us to share our learnings with others. It's only by doing this and sharing our experiences that we can help other people and other companies. So in the course of the presentation, we'll talk about process safety information, the background to the process. Then we'll look at the process safety risks, but we'll focus on the runaway reaction risk. And within assessing runaway reactions, we'll look at systematic assessment procedures, what they should look like and why you should have one. And then specific to the case study, we'll look at thermodynamics and thermal stability, how we identify and assess potentially hazardous scenarios, and then how we rigorously evaluate those scenarios using layers of protection analysis to prove the validity of the safety case. We conclude with some relief system considerations for what is a rather demanding runaway reaction, and then we'll seek to summarise all of these things together. We'll start out looking at the background to the process. The process involves the epoxidation of vegetable oil via the Prillis-Jehu reaction, where peroxyformic acid reacts with the unsaturated double bonds in the vegetable oil to form the epoxy group. This is a very long established process and also very widely used. The process conditions involve mixing oil, solvent and hydrogen peroxide at 65 degrees, adding formic acid in a semi-batch manner over 120 minutes, and as you'll see from the reaction mechanism, the performic acid reacts with a double bond, liberating the epoxy group, but also rejuvenating and regenerating the formic acid. So the process involves the addition of further hydrogen peroxide, reacting out for a further 5 hours, and then quenching the batch. The regulators in the UK challenged the safety of the process after more than 50 years of processing on site. There are a number of key learning points through the process. The first one being that a history of incident-free operation over a number of years isn't a guarantee of an incident-free future. In process safety, we're looking at events which are extremely low probability, but can be extremely high consequence. So we should strive for a culture based on a chronic sense of unease. The second key learning point is that operating companies must be confident that their process safety studies are able to withstand scrutiny, either through the provision of internal competence, using external specialists, or a combination of both. and processes should be regularly reviewed against current standards and best practices to ensure that the safety case is current and up to date. Next, we'll look at the process safety risks involved in the process. So there are a number of significant risks posed in this particular process. The first one, and the one that the operating company in this case had focused on most of their attention over the 50 years, was the potential for detonation. Hydrogen peroxide, formic acid and water mixtures can be detonable. The triangle diagram in the top right hand of the screen shows the region of instability or detonability of the hydrogen peroxide and formic acid mixtures. The wiggly blue line that's been superimposed demonstrates the process composition throughout the process, which has been specially designed to stay out of the detonable region indicated by the red line and the highly hazardous region indicated by the orange line. There is, of course, always a flammable solvent risk with such operations. And there's also a risk of oil oxidation, sometimes called oily rag syndrome, where finely divided oil, either soaked into lagging or on cloths, can almost spontaneously combust. And vegetable oils are particularly renowned for that type of behaviour. The final risk, and the thing that we're going to focus our efforts on, is the risk of runaway reaction. The next key learning point in the case study is that you must have a safe system of work in place to protect against all foreseeable risks. You can't focus on the main risk and ignore the others. So now we'll look deeper at the runaway reaction risks and go through the systematic assessment procedure, look at the kinetics, thermodynamics and thermal stability of the process, look at assessing hazardous scenarios, and then rigorously evaluate those, and then consider the relief system. So having a systematic assessment procedure ingrained in process development is a really pivotal safeguard against exothermic runaway reactions. And this assessment procedure starts before any synthesis. It starts at the chemical route selection stage, where the selection of the chemical route can be governed to some extent by the process safety risks that the synthesis may involve. At this stage, we'll be looking at things like predicting the heat of reaction, and if we can get that, predicting what the adiabatic temperature rise is, and then predicting what the maximum temperature of the synthesis reaction might be. We'd also look, in terms of thermal stability here, for potentially unstable functional groups. When we do get into process development and optimization, hopefully of a route that's been selected with a balance of good process safety characteristics, we'll be looking to fully characterize the normal process. That's measure the heat of reaction through calorimetry, quantify any gas generation, and be able to measure and calculate the adiabatic temperature rise. In terms of thermal stability, we'll look at explosivity risk assessment if there are very unstable functional groups present, look at preliminary thermal stability screening, and then hopefully be able to do further testing to define maximum safe process temperatures. Once we get to pilot scale, and then again at production scale, we need a basis of safety to exist. This will involve a process of identifying what hazardous deviations can exist, then simulating those deviations or modeling those deviations to understand the consequence, and then putting in place safety measures to either prevent the hazardous deviation from occurring or to protect against the consequences of that deviation. This process is shown twice here, once for pilot scale and once for large scale. And that's very intentional because the risks at each scale are different. Pilot scale operations use different plant, different control philosophy, different extent of manual intervention than large scale plant. So it's very important that you do this process twice. The key learning point here really is that the systematic assessment process should be ingrained in process development and should start before any synthesis begins. For retrospective process assessments, making sure that you fill in any gaps with missing characterization data will optimize the effectiveness of decisions made when considering consequences in the subsequent process hazard analysis. In the first stage of reaction hazard assessment here, we're looking to characterize the overall thermochemistry of the process, and there are lots of potential energetic reactions which can occur. The desired epoxidation has a heat of reaction of between -230 and -250 kilojoules per mole. There's gas generation in the second stage, there is significant accumulation of reactants, and the potential adiabatic temperature rise of the process is 330 Kelvin. The worst case composition in terms of runaway reaction potential occurs after the second hydrogen peroxide addition, where 51% of the reaction takes place after the peroxide addition is completed. There are also other energetic reactions possible. The decomposition of hydrogen peroxide has a heat of reaction of -98 kilojoules per mole, and the decomposition of the performic acid has a heat of decomposition or heat of reaction of -350 kilojoules per mole. The graph on the right-hand side shows the METTLER-TOLEDO RC1E simulation of the normal process, the dark blue line indicating the heat flow, and you can see very clearly here two peaks. The first associated with the first stage of reaction during the formic acid addition, and then a second spike after the addition of the second portion of hydrogen peroxide. And it's the accumulation after that second hydrogen peroxide addition that is most interesting for us in terms of runaway reaction potential. The very light blue line at the bottom of the graph also demonstrates the gas generation from the process. You'll see from the tail of the heat flow, also corroborated by the gas flow information, that the desired reaction takes 5 to 6 hours to reach a high degree of completion after the second peroxide addition. The key learning point here is more in terms of chemical engineering. While chemists focus on thermodynamics, engineers tend to focus on kinetics because it's kinetics which drive vent size. Regulators increasingly seek not just the thermodynamic information, but also kinetic information when inspecting multi-product plant to ensure that worst-case reactions are known. Just comparing heats of reaction provides a basis for hazard analysis, but not for risk assessment. The next step of chemical reaction hazard evaluation is to understand the thermal stability of the batch. So you'll see here a thermal stability test using accelerating rate calorimetry, an adiabatic calorimetry technique, and a sample of the batch after full completion of the reaction. You'll see the classical heat weight search analysis of the ARC technique, indicating nothing occurring up to about 270 degrees, and then a slow initial but accelerating very rapidly exothermic decomposition with considerable pressure generation. Correcting for 5-factor effects, the TD24, or the temperature from which it takes 24 hours from onset to reach maximum rate, is calculated to be 238 degrees C. Key learning point here is that isothermal calorimetry measurements only tell us half the thermal story necessary to understand the safety of the process. Understanding the thermal stability is an absolutely essential ingredient in understanding the overall risk. Once we've characterized the process in terms of reaction calorimetry and thermochemistry understanding and thermal stability analysis, it's necessary to look at the plant together with the process to identify potentially hazardous scenarios. There are a number of methods which can be applied to do this hazard analysis. We could use conventional hazard and operability studies, what-if analysis, failure mode and effect analysis, a simple checklist, fault tree analysis, or some other bespoke chemical reaction hazard analysis. For the process involved in the epoxidation, there were 9 significant deviation scenarios identified. The first one being the least complex, the most foreseeable, which was cooling failure at the end of the second peroxide addition. After that, 8 other scenarios were also identified which could lead to runaway reaction. These hazardous scenarios have to be identified rigorously, avoiding assumptions and cognitive bias. The process of performing a subsequent layer of protection analysis on each of these potential deviations provides a good basis to educate the stakeholders that all safeguards are not equal, some having a very finite and in some cases very limited reliability, some having a minor contribution to the overall protection, but others having a very high importance. Having identified potentially hazardous scenarios, it's necessary to simulate and quantify those scenarios. In this case, we've looked at the adiabatic simulation of the loss of cooling scenario at 51% accumulation of peroxide. This test was conducted using a VSP2 adiabatic calorimeter in a passivated Hazardous cell with a 5 factor of 1.1. You can see in a small matter of minutes the reaction progresses and just over 100 degrees accelerates extremely rapidly, generating very high pressures, in this case well in excess of 70 bar. One other protection mechanism that existed on the plant was a water quench. In the laboratory, we can use our adiabatic calorimetry techniques to look at the effectiveness of the water quench. And you can see in this graph side-by-side comparison of the temperature and pressure profiles when the water quench is added to the 51% accumulation scenario when the temperature reaches 90 degrees. The red lines represent the unquenched reactions, the blue lines represent the quenched reactions, and you can see the downturn at about 90 degrees as the water is injected. What you will also see is that the water injection does not kill the reaction. The reaction continues. The peak temperature is slightly moderated, the peak pressure is slightly moderated, and the rates are slightly moderated, but a runaway reaction still continues to well above the design pressure of the plant. The key learning point from this stage of work is that the physical water quench doesn't stop the reaction. The reaction continues, but at a lower rate. So this buys us time and to a lower peak conditions, but possibly still hazardous. So the summary is safeguards don't just need to operate, they must be fully effective in removing the hazard. Without wishing to dwell on the detail, I wanted to show you an example of what a layer of protection analysis looks like for scenario 1. Scenario 1 is failure of the cooling water supply at a point in the process immediately after the second hydroxide charge, leading to runaway reaction, overpressurization, vessel rupture, and in all likelihood resulting in the fatality of the 2 operators who supervise the plant. Firstly, we look at the initiating causes and their likelihood. The potential causes here were cooling pump failure, electrical failure, control failure closing the cooling supply, agitator failure, or cooling water pipe rupture. Overall, the likelihood is about 1 per 4 years that this event would occur. Then we move on to look at the protection layers in place. Firstly, we have general process design. The process is not in this at-risk state all the time over the course of a year, but for 1750 batches per year with a risk period of 2 hours per batch, we can see that about 40% of the time we are at risk. We also have a SIL compliant quench system for which we can take credit. We have really good evacuation procedures in the event of an emergency. And if we have an adequately sized relief system, we can take account of a reduction factor of 100 in the likelihood. The conclusion for this study is that the risk is as low as reasonably practicable if the relief system is shown to be effective. The risk is the sum of all the scenarios, not just this scenario. The key learning points here are firstly, that just because a vessel has a vent doesn't mean it's big enough. And secondly, even if you have a vent, you're now only recommended to take a risk reduction factor of 100 if it's adequately sized. Emergency relief systems are very commonly the ultimate basis of safety for many reactors involving exothermic reactions. But there are some considerations that need to be taken into account to make sure that the relief is doing and will do its desired function. Firstly, the relief system for a runaway reaction has to be based on Dyer's methodologies for two-phase discharge. Dyer's is the Design Institute for Emergency Relief Systems. In the current case, the Quench is a very necessary layer of protection to meet the tolerability criteria. As we've seen earlier in the case study, the Quench does not stop the reaction, but it does slow the reaction down, and slowing the kinetics provides a realistic way of reducing the size of the emergency relief device that's required. But still, having a 0.5 meter diameter vent, the thrust forces seen on the pipework by the two-phase flow are huge, and you must have adequate support and bracing in this pipework to ensure its integrity. Finally, the discharge normally has to be captured in a suitable separation device, like a dump tank. That also needs adequate design for separation. In the current case, because of the diameter of the pipe, bends in the pipework could not be supported due to the extreme thrust forces, so the pipe had to direct directly and straight into a dump tank. Final learning point in the case study, therefore, is that designing a relief system is way more complicated than just sizing a hole correctly. Now we come to the summary. So the idea of this case study was to look at the end-to-end way that we safeguard plants and people against the effects of runaway reaction. We've pulled out a number of key learning points throughout the case study, and we'll go through them here one at a time. Hopefully these will be useful for you. They were certainly useful for the operator. The first key learning point was that an incident-free operation in the past is not a guarantee of an incident-free future. Secondly, process safety studies must be current and able to withstand scrutiny. In terms of current, that means being refreshed regularly to reflect current best practices. Third point is that a safe system of work is required to protect against all foreseeable risks. You can't just focus on the highest risk and protect against that and ignore the others. Fourth, a systematic assessment process for reaction hazards should exist. That systematic process will give rigor to your attempts to protect your plant and people against runaway reactions. Any gaps when you're doing a retrospective assessment should be filled. The fifth point was that kinetics drive vent size. Heats of reaction are not a good way to compare reactions in terms of vent requirement. Sixth is that isothermal calorimetry and thermal stability together are needed to understand the overall thermal risk of a process. Hazardous scenarios must be rigorously identified, avoiding assumptions and cognitive bias. The eighth point was that physical quenching doesn't stop a reaction in all cases, but it can slow them down, and it does slow them down in this case, so that we can get a realistically sized relief device. The ninth point was that just because a vessel has a vent, it does not mean it's adequate. The vent has to be adequately sized for the kinetics of the reaction that's occurring. And even if we do have an adequately sized relief system, that only provides us with a risk reduction factor of 100 based on latest information. So a relief system is critical to meeting the tolerable risk criteria, but it's rarely adequate on its own without other layers of protection. The final point was that designing a relief system is way more complicated than just sizing the hole correctly. So in conclusion, there are a number of steps that we have to go through in assessing the safety of a chemical process. We have to understand the thermochemical properties of the reaction, that's thermal stability and reaction calorimetry. We need a robust method for looking at process hazard analysis, looking for potential worst case scenarios. Then we need to look at the consequences of those scenarios and then ensure that we have safeguards in place. And in this case, we had a quench of which we've proven the efficacy, and that was a SIL compliant quench system. And we have a relief system, and we've looked at the sizing, the mechanical strength of the line, and separation of the discharged material into a containment vessel. And then we've got to demonstrate that our residual risk is acceptable against our own risk criteria, and we've demonstrated the use of LOPA in this study to do that. So in assuring the safety of an exothermic reaction involves many interrelated and multidisciplinary steps. A failure or an error in any of those steps can compromise the overall safety of the process. A final reflection on the case study is that we've demonstrated here that even very hazardous reactions can be operated safely, but the process of assuring safety for these processes can be, and usually is, very demanding. A better way is to develop inherently safer processes, to operate nearer the top of the hierarchy of controls. And this is where chemists come to the fore. Chemists build in risk to the processes by virtue of the synthetic routes that they choose and the raw materials that are involved. Engineers then have to control those risks. So process safety awareness for chemists is pivotal to empower them to make more informed decisions in development. Thank you very much for your attention. Thank you for watching, and I look forward to any questions that you may have.